All right, we're back and we're live again, ready to do your office hour for calculus questions. This is probably the topic I get the most questions about, so I'm excited to dive in as we give people a chance, though, to log in before we get going. So hopefully you're all logging in on all of the different streaming devices. We are excited to have you here today to join us for our live. So a big hello to everyone who is rolling in right now. Welcome to our live office hour for calculus. That's right, brought to you by Chegg. I'm at Wallace Stem. You probably know me from my channels at Wallace Stem on TikTok, Instagram, Twitch, and beyond. And I've been teaching calculus for probably about 10 years, maybe even 20 years. We won't talk about how old I am. That's probably best. For those of you that have joined our live events before, though, welcome back. We are excited to have you back again. But for those of you that are here for the first time, the goal today is to help you understand your calculus course and concept. I'm going to be here each week at this time. It's 4:15 Pacific time, 7:15 Eastern time, every Thursday to do just that. So mark your calendars. You can also scan this QR code in the corner, and that way you can be up to date on all of our live office hours. But this Chegg Calculus live office hour is 4:15 Pacific time, 7:15 Eastern time every Thursday. So mark your calendars and make sure you join us as we're here to help you with your virtual office hour. I'm here to help. So make sure any questions you have end up in the chat, and I will do my best to answer as many of those chat questions as I can. In fact, there is one question from last week that I did not have time to answer. So we're going to start with that. And then as you're logging in, stick those questions in the chat and I'll make sure I answer them as the hour goes on. The question had to do with products inside of the integral. So that product problem was something like x squared sine x dx. That's what the user submitted to us, I think from TikTok. And so in order to solve a product, there's really a couple ways we can go about it. One of the most common ways, though, is integration by parts. Integration by parts is essentially the product rule from differentiation done backwards. There's a little more to it than that, but that's essentially what we've got. When we've got a product, we're going to pick one piece to be the u, maybe the x squared, and the other piece we're going to call dv, which is the sine x dx. Then we can take the derivative of the u. The derivative of u is 2x's dx. And to get the dv, we're going to take its antiderivative, which is going to be v, is going to be negative cosine of x. Do I also do questions from Calc 2 or just Calc 1? I do all Calc 1, 2, and 3. So have those questions come in whatever class you're in. Let me know what class you're in. I'd love to hear and how it's going, but also what questions you have, and we'll take a look at those. For this one here, though, we're doing integration by parts. The integration by parts formula says we take u times v and we subtract the integral of v du. Some people like to remember it's ultraviolet voodoo. If you speak Spanish, you could say it's una vaca vestido de uniforme. However you want to remember it, I like to remember it visually, that we do the diagonal and we subtract the integral of that horizontal. However you remember, it's great though. I'm going to take x squared times negative cosine x, which gives me negative x squared cosine x. And then I'm going to subtract the integral of v du. A negative times a negative is going to make it a positive. And then I have 2x times the cosine of x dx. Well, we end up with an integral that hopefully is going to be easier to solve. Well, it's closer, I guess we could say, but it's not quite what we want. We're going to do integration by parts again. We went from x squared to just x. We'd rather not have any x's in there at all. So let's make the u equal to the 2x, and the du, its derivative then is 2 dx. dv then is everything else, the cosine dx. We take the antiderivative to get v. The antiderivative of cosine is just the sine of x. And then we can do much the same thing. We're going to take u times v, and we're going to subtract the integral of v du. When I do that, don't forget we've got this negative x squared cosine x out front. Plus, we're going to do 2x times sine x. That's the u times v. And then we'll subtract the integral of v du, 2 times the sine of x. And if we've done this all right, that's going to be, oops, sorry, got a pop-up on my screen. That's going to be an integral that's going to be easier to take the antiderivative. And sure enough, it is. We know the antiderivative of that function. So we've got negative x squared cosine of x plus 2x sine of x minus 2, and the antiderivative of sine is negative cosine x, which changes that to a plus. And of course, we always remember the plus c at the end of our integral. Now, this is the official formal way to do integration by parts using that formula where we take the integral of v du is equal to u times v minus the integral of, the integral of u dv is equal to u times v minus the integral of v du. That's the official legal formula that one should use on the AP test. A lot of your calculus instructors want you to use that formula, but I'm not going to gatekeep. There is a shortcut with integration by parts that works really well when we've got a polynomial that's going to take a derivative down to 0. Let me show you this cool little trick, and it's going to give us the same exact answer. We can take derivatives of the x squared. Its derivative is 2x, whose derivative is 2, whose derivative is 0. We're going to take derivatives down until it goes to 0. Then we can take antiderivatives, or integrals, of the second part, which was the sine of x. Sine of x has an antiderivative of negative cosine of x, who has an antiderivative of negative sine of x, who has an antiderivative of cosine of x. Then, to get our final answer, all I'm going to have to do is multiply these diagonals together and alternate the signs. It's going to start positive, then negative, and then positive. So positive times a negative is going to make a negative, and it gives us x squared cosine x, which is our first term. The second term is a negative times a negative, which is going to make it a positive 2x sine x. That's our second term. Then we've got a positive 2 times the cosine x. That's our last term, and you always remember the plus c. So this is a nice little trick to kind of check your answer if you want to check your answer with it. Or maybe some of your instructors are going to be nice and they're going to actually let you do that as well. So that is integration by parts. It's a product. That's one of the great integration methods. We didn't have time to answer it last time, but I see a lot of great questions coming in the comments. I really love seeing the questions. Keep those coming. I'm going to answer as many of them as I can. I'm going to start with at Smiley Face on TikTok. We're going to look at a double integral. In fact, can I up you one? Let's look at a triple integral. I'm going to erase this, though, really quick so that we can do just that. As I'm erasing, remember, this is Cheg's Live Office Hour. We're here every Thursday at 4:15 Pacific Time, 7:15 Eastern Time to answer your questions. So keep those questions coming. We're going to integrate from 0 to 1, the integral from 0 to z, the integral from 0 to x plus z, 6xz dy dx dz. So I'll never fail to deliver here. You ask for a double, I'm going to give you a triple. We'll up it one. It's really the same idea. We're just going to do one more step of that exact same thing. So when we have multiple integrals, really what we're doing is we've got problems kind of nested inside of each other. So the first nest is going to be this integral right here. That's just dy, which means our variable is actually y. And then we're going to treat the others like a constant. So these are both constants. So this is really just a constant dy, whose antiderivative is that constant times y integrated from 0 to x plus z. And this is what's equal to y. So we're going to replace the y with x plus z. And we can replace the y with 0. That's going to give us 6xz times the y, which is x plus z. And then we subtract. When we plug 0 in, the whole thing goes to 0. And so that becomes our solution to that first step. Well, let's do a little algebra. Let's simplify it. Let's distribute. So we're going to have 6x squared z plus 6xz squared. Now this is going to have wrapped around it the second integral, which is going to be the integral from 0 to z dx, which means now x is my variable, and I'm going to treat the z's like they're a constant. So when I look at this first term, x is my variable, I'm going to increase that exponent by 1 and divide by the new exponent, keeping the z constant there. 6 divided by 3 is 2. Plus, x is my variable. I'm going to increase that exponent by 1 and divide by the new exponent, 3x squared times z squared. And then we're going to integrate this from 0 to z. And of course, that's what x equals. So we're going to plug in for these x's a z, and then subtract, plugging in the 0. So we've got 2, plug in the z cubed times z, plus 3, z squared times z squared. Then we subtract, plug in the 0 in, but we really like the number 0 because 0 times anything is 0, 0 times anything is 0, so we're actually just subtracting 0. Combining like terms, because that's really z to the 4th and z to the 4th, we have 5 z to the 4th is the solution to that second level integral. And then we just do it again. We're going to integrate the outside integral, which is an integral from 0 to 1 dz. Well, this is just a basic integral. We can increase that exponent by 1 to get z to the 5th. Divide by 5 gives me just 1, and we're integrating from 0 to 1. That's almost too easy at this point. Plug in a 1, 1 to the 5th is 1. Plug in a 0, get 0. And that tells us that that kind of 4-dimensional volume area thing has an area of 1 underneath that 3-dimensional shape. Excellent. Great questions coming in the chat. I saw something about trig integration. Let's see if we can do some trig integration and maybe some U integration. Great questions coming in. Keep them coming. Remember, we are here to answer your questions every Thursday at 4:15 Pacific time, 7:15 Eastern time. Question came up, wanted to see some trig substitution. When do you use trig substitution? How do you know to use trig substitution? That's a great question. The way we know how to use trig substitution is whenever there's a square root that's really annoying in the problem that we want to get rid of. So if I've got the square root of 9 minus x squared over x dx, it would be really nice if that square root was not part of the problem. That's what we're trying to do with trig substitution. We're trying to get rid of that square root using one of our Pythagorean identities. And the Pythagorean identity that works, if I think about this like the number 1 minus x squared, that's like 1 minus cosine squared or 1 minus sine squared. So that's going to be our substitution. Let's do, we take the square root of the 9, which is 3. And with the subtraction, we'll do sine of x, because that's going to make this 9 sine squared. And it's going to simplify to a cosine squared under a square root. It's going to simplify real nice. That's why we do it. Dx, the derivative of 3 sine is 3 cosine. And then we just substitute that into the equation. Ooh, whoa, moving too fast. We shouldn't use x both times. Let's change the variable to theta. That way we don't forget to substitute back to our original x's. I'd hate to stop too soon. All right. So this integral then is going to become the integral of the square root of 9 minus x squared. Well, x squared is going to be 9 sine squared of theta. All over the x, well, x is 3 sine of theta. Dx, which is going to become 3 cosine theta d theta. Now, why do we use sine? Great question. We could use cosine. Cosine kind of accomplishes the same thing. The thing we don't like about cosine is the derivative of cosine is negative sine, and so we've got to worry about positives and negatives. And if I can avoid making a negative error, I'm going to do that every time. Why did I choose sine instead of like tangent or secant? Great question. The reason is because on this next step, if I look at simplifying this square root, I can factor a 9 out of the square root or under the square root, and that's going to leave me with 1 minus sine squared of theta. So I've replaced that with 9 times 1 minus sine squared theta. And the reason we picked that is when I do 1 minus sine squared, that's a Pythagorean identity. That's cosine squared. So this can even simplify further to 9 times cosine squared of theta. And then I can actually take the square root. I'm running out of space, so might as well just recopy the whole integral. The square root of 9 is 3. The square root of cosine squared is cosine, or times 3 cosine all over a sine, 3 sine of theta, d theta. Whew. Did I do something wrong? We're going to simplify out of 3. That's obvious, right? We're going to reduce out of 3. Boom, boom. Then we've got cosine squared over sine. Oh, yeah, that's not too bad. Cosine squared over sine is not too bad at all because cosine times cosine is cosine squared. That's the same as 1 minus sine squared theta. And we'll put that over sine of theta d theta. And then we're going to do a little bit of simplifying to get to our answer. Exactly right. I see a comment from Clouds in Oakland on TikTok. Secant, sine, and tangent have the positive derivatives. That's why those are the ones that we use when we're doing a trig substitution. We just like to avoid that negative. You can deal with it if you want. It'll work. But I'm going to divide this sine by both of these parts. That's going to give me 3 times the integral of 1 over sine is the cosecant of theta. Sine squared over sine is the sine of theta, d theta. And we can do that integration quite nicely. Let's go ahead and do it. We're going to do, oops, I already did black. Let's go blue. We're going to distribute the, well, let's not. Yeah, let's distribute the 3 through. 3 times cosecant is natural log of cosecant plus the cotangent. 3 times negative sine is negative 3. Antiderivative of sine is cosine. Actually positive, because cosine has a negative sine derivative, plus our constant. Now, this is our answer in terms of theta. We don't want an answer in terms of theta. We want an answer in terms of x. And so we're going to use this x over here to build us a triangle off of this angle theta. If I divide 3 on both sides, we see that the sine of theta is x over 3. Well, we know that sine is opposite over hypotenuse. So that gives me 2 sides of a right triangle, which now I can take the Pythagorean theorem to find out the other side is 9 minus x squared, the square root of that. Why doesn't it become an absolute value when I take the square root? You're talking about this square root up here? It should be a positive because it came from the problem. I didn't take the problem. I didn't take the square root. Oh, you mean here. Yeah, that should be an absolute value technically. But we're not going to worry about that domain restriction here because we want to illustrate the trig sub here. So we've got our triangle. We're just going to plug into here and evaluate each of these trig integrals or these trig ratios using this triangle. So do I still have room on the screen? I do. We've got negative 3 natural log of cosecant is hypotenuse over opposite, 3 over x, plus cotangent is adjacent over opposite. That's the square root of 9 minus x squared over x, plus 3 cosine, that's the square root over 3. And when I divide by 3, that's gone. And so that's going to be my final solution there. So trig substitution is all based on getting rid of that square root. As we were doing this trig sub, I saw several comments, though, that wanted to take a look at just regular u substitution. So let's back off of the trig sub and take a look at some u sub problems. U substitution is probably the most used integration method that we're going to see. It's really doing the chain rule of derivatives backwards. So let's take the integral of, let's do, well, want to pick a good one. Let's do x cosine x in the denominator. Let's do cosine x minus x sine x in the numerator, dx. Maybe the way I built it made it a little more obvious what's happening, but that's okay. The whole idea of u substitution is we are looking for dx to be multiplied by the derivative of a part of the problem. So here, if I were to make this bottom part u as the x cosine of x, its derivative du, ooh, careful, that's a product. Make sure we're using our product rule. Good time to review the product rule. The derivative of the product is the derivative of the first times the second plus the derivative of the second times the first. The derivative of x is 1 times cosine of x plus the derivative of the second. The derivative of cosine is negative sine times the first, which is x, dx. And you notice that is exactly what's up here multiplied by the dx. So what ends up happening, and actually I'm going to color code this a little bit better. So we'll write this du is cosine x minus x sine x dx. What ends up happening is this denominator is all going to get absorbed into the u. And the numerator, this cosine x minus x sine x dx, all gets absorbed into the du. And that simplifies the equation down to something that we can solve. 1 over u du, that's just the natural log of our u. But remember that u has a special value. That u is this x cosine x. So for our final answer, we can say it's the natural log of that u plus c, or the natural log of the x cosine x plus c for our final solution. Excellent. Great question coming in, wanting to look at the washer method. It's a great application of integration. So why don't we take a look at it and erase this u substitution problem. If you want to see more u sub, put it in the chat. Let us know. We can do some more involved problems, maybe some where we have to actually solve for the x in order to do the full substitution or something like that. So let's take a look at the graph of y equals x squared and y equals, let's do y equals x. Let's see what that looks like. So y equals x squared. I'll do this one in blue. That's this graph right there. Y equals x. I seem to always drop my pens on these lives. You gotta watch me go and get them. It's like I'm on stairs. No, not really. Okay, we'll go back to the problem. Y equals x. Y equals x is a straight line coming right out of the center. And it kind of creates this disc-looking thing. And we're going to rotate it around one of our axes. Let's go ahead and rotate it around the x-axis for now. If I rotate it around the x-axis, it's going to end up looking like this. And it's going to have that curve there. That's sort of the same thing. Don't judge my 3D drawings. And because it is round, it's going to be like this. So it's kind of like a cone, but we've kind of dug out the center with this horn-shaped thing looking in there. So that's what we want to figure out the volume of. Now, there's really two ways to do this. One is by washers, and the other way is by cylindrical shells. If we have time, we'll take a look at both, but you specifically asked for the washer method. So let's look at the washer method. The idea of the washer method is I can look at a slice of this shape cut out, and it's going to be a washer. Not like a washing machine, not like a cleaning thing. A washer is one of those round things that you put underneath the bolt. That washer is round with a hole in it. That's what we're saying the washer is, this round thing with a hole in it. And that's going to be what we're interested in. Well, the shape of it is a circle with a hole cut out. Well, a circle is pi times the radius squared. And we're going to say it has a little tiny width of dx. then what we're going to do is we're going to take this disk. Well, let's first figure out it's got a big radius going up to this red line, going up to the x. And we could figure out then that would give us the area of the cone. But then we want to subtract off the radius squared of the center circle. That's going to the blue line of the x squared. We're going to add up all of these circles as this disk slides back and forth. It's sliding up and down the x, so that supports a dx integration. It's going to start here at 0, and it's going to go up here till the two graphs meet each other. Well, we need to know where the two graphs meet each other. We need to know if these both equal y. We need to know when x squared is equal to x. Well, if I subtract x from both sides, I get x squared minus x equals 0. And I can factor out the common factor of x. And we can see x is 0 and 1, which means it's going to intersect at 0 and this value up here. That's at 1. So we're going to integrate from 0 to 1. It's really the area of a circle, pi times the radius squared, minus the whole, which is pi times the radius squared. Oops, I didn't square that one. There we go. Somebody catch that in the comments? Yep, all right. So let's solve it and see if we can figure out what the volume is of this washer revolving around. We've got pi times, this is x squared. So that becomes x cubed times 1/3 minus, this becomes x to the 4th when we multiply those exponents together. So we increase the exponent by 1 and divide. And we're going to integrate that from 0 to 1. So let's plug that in. Top of 1 cubed, 5 cubed, those are nice. It's just 1, so 1/3 times 1 minus 1/5 times 1. Plugging the 0 in is also really nice because 0 and 0 is 0, so there's nothing really to subtract. And then all I need to do is combine the fractions, get a common denominator, which is going to be 5 and 3 over 15. 5 minus 3 is 2/15 of a pi. That is going to be the volume of this thing rotated around using washers. Excellent. Hopefully that helped answer that question. Let's see, what other questions do we have? We had to integrate over a differential form like the dx wedge dy. I don't think I know what you mean by wedge dy. Maybe you could be more specific. How about the integral of x squared over x to the 4th plus 1? That's going to be an ugly one. We're going to put that one off. Excellent. We did that washer method. Trig sub's very cool. The square root of cosine squared, isn't that just cosine? Yes, it is. We did some u sub. I know I saw a topic in here that I missed. Keep your comments coming. They are so great. Let's go ahead and take a look then at some partial fractions. Yeah, that would be excellent. From TikTok, wanted to see some partial fractions problems. Partial fractions is one of my favorite integration methods. One, because I think just the solving of them just is so cool how we can break them up. Let's do a partial fractions problem that might be just kind of a little bit more interesting. Let's do the integral. Let's just do dx in the numerator of x minus 1 times x squared plus 1. We've got that irreducible quadratic in the denominator. So when we break up that irreducible quadratic, yes, we're going to do a fraction for the x minus 1. But when we've got x squared minus 1 in the denominator, or x squared plus 1, sorry, minus 1 would have been much nicer. We don't have that. When we've got x squared plus 1, we can't factor that anymore, so we need to do a bx plus c. We've got to account for every power of x that's smaller than the leading power. So we've got x to the 1st and x to the 0 we have to account for. We're going to split this fraction up, so this fraction needs to be equal to the original fraction, which is 1 over the x minus 1 times x squared plus 1. So let's go ahead and solve this. We're going to solve it by multiplying by this common denominator. So the x minus 1's reduce out, and we're left with a times x squared plus 1. Plus, we'll have this bx plus c. And it's going to get multiplied by the common denominator, but the x squared plus 1 will divide out, leaving just the x minus 1. Both of them divide out over here, and we're just left with 1. Lots of ways we can go about solving from here. One thing that's nice is this equation is true regardless of what x is equal to. So I can pick whatever convenient value for x I want, which means if I pick x equals 1, this goes to 0, which makes all of this go to 0. So if x equals 1, I get 1 squared plus 1 is 2 times a. All of this goes to 0, and it's equal to 1, which means a I now know is 1/2. Excellent. Let's pick another convenient value for x. If x is 0, bx goes to 0, and so this is gone. So if x is 0, I've got 0 plus 1 is 1a. We already know a is 1/2. Plus x is 0, this becomes negative 1. C is equal to 1. Well, if I add c to both sides and subtract 1, I find out c is negative 1/2. We've got c. All we have left to do then is find our b value. I see a comment about series. That reminds me, I missed a comment about series last time. So we're going to go back to series after this problem. So stay tuned, stick with us, and we'll do series next. Let's make x equal to negative 1. If I do that, I got negative 1 squared, which is 1. 1 plus 1 is 2. 2 times a, 2 times 1/2 is 1. Plus negative 1, so we've got negative b, plus c, which is negative 1/2, times negative 1 minus 1 is negative 2, equals 1. This is really nice because when I distribute the negative 2 through, we get 1 plus 2b plus 1 equals 1. Subtracting the 2 from both sides, 2b is equal to negative 1. So b is negative 1/2. All right, what we have just done is we have split up this integral then into two separate integrals. One that has a denominator of x minus 1, and one that has a denominator of x squared plus 1. A is the numerator of 1/2. I'm just going to go ahead and pull the 1/2 out because that's a constant. B and C are both divisible by 1/2, so I'm going to factor out that negative 1/2. So I'm going to make this minus 1/2. And then B was 1 and C was 1, so x plus 1 dx. That's going to give us two integrals that we're going to solve, but I need some more whiteboard space. So if you want to screen capture the solving of this, now's the time to do that because I'm going to erase all of this so that we have some space to actually solve these two integrals that we just got. All right, the first integral is easy. The first integral is just the natural log of x minus 1. The second integral, we're going to do a little bit more creative work with. We're going to ultimately try to make a u substitution where u is equal to the denominator of x squared plus 1, which means du is 2x. I don't have 2x. I have x plus 1. This is where we're going to get a little creative. We're going to multiply by 2 and then split that into two fractions. When I multiply by 2, that's going to become 2x plus 2. Well, multiplying by 2 has to be offset by dividing by 2. So now my problem has become 1/2 of the integral of 1 over x minus 1 dx minus 1/4 times the integral of, I'm going to take this x plus 1 and divide it by the two parts separately. So we've got the 2x over x squared plus 1 dx minus, we've got the 1/4 times 2 is 1/2 times the integral of 1 over x squared plus 1 dx. We have now split the original integral into three separate integrals, and we should know exactly how to solve each of the three integrals. Let's do it. Final answer is 1/2 natural log of x minus 1 minus 1/4. Remember, we set this up so that this would become 1 over u, which means it's the natural log of the denominator, x squared plus 1, minus 1/2. This should be an integral you recognize. It is the tangent inverse. So it's 1/2 tangent inverse of x, or if you prefer arctangent of x. And of course, nobody's going to ever forget. What do you not forget? Plus c to finish it off. That's partial fractions. Thank you for that question. That was a fun one. I did one that was a little bit more involved, but I do see some questions about convergent series. So let's take a look at convergent series, and then maybe we'll come back to some integration by parts and talk about some strategies with integration by parts. Remember, we are here every week, every Thursday at 4:15 Pacific time, 7:15 Eastern time. Mark your calendars so you can join us. Scan the QR code in the corner so you don't miss future lives. We have such great questions and discussions about calculus helping in your class as it progresses. We're going to be here all semester long, so make sure you don't miss out. I mentioned we were going to do some series, and there was specifically a request for alternating series. So let's take a look at the sum as n goes from 1 to infinity of -1 to the n times 1 over 4n minus 1. And we want to know, we don't really care what the answer is. What we really want to know is, does it converge or does it diverge? When we have a series, usually an alternating series, because we got that -1 to the n, making it positive, negative, positive, negative. When we have an alternating series, the first thing we want to do is see, does it converge? Absolutely. In other words, if we ignore the alternating part, does this converge? Because if it converges absolutely, let's say it converges absolutely to 12, alternating is just going to make it bounce back and forth to something smaller than 12. So that's a good thing. So let's look at the sum as n goes from 1 to infinity of 1 over 4n minus 1 and try and decide if that converges or diverges. Hopefully it converges. Well, this is really close, really similar to 1 over n, which is the harmonic series. That strikes fear into me because the harmonic series diverges. So it's already kind of dicey. But let's do the limit comparison test, where we take the limit as n goes to infinity of my unknown series, 1 over 4n minus 1, and divide it by a known series that's similar to it. Let's divide it by 1 over n. Okay, I'm going to simplify this. Technically, there should be absolute values, but I think everything's positive, so it doesn't matter. That's the limit as n goes to infinity of n over 4n minus 1, because I multiply by the reciprocal. And as n gets huge, this goes to 1/4, because that minus 1 doesn't really make a difference. How the limit comparison test works is if this equals a number besides infinity or 0, then both the numerator and denominator are going to do the exact same thing. Well, I know 1 over n diverges. That's the harmonic series. We can prove it diverges using the integral test if you want. So if the bottom one diverges, the top one diverges as well, which is exactly what we did not want to happen. Because if this converged, then I would know the alternating series converged. So all of that work, and we gained nothing. But we could see if this is a conditionally convergent series. A conditionally convergent series, we just need to show that the next term is smaller than the current term. Because the idea is, if I go positive some direction to this point, and then the next term is smaller but negative to this point, and then the next term is smaller but positive, goes to this point, and then it just keeps getting smaller, what you're going to see we do is it's eventually going to converge down to a point down here. Because every term is smaller, we're just kind of zooming in on the actual value. So that's what we're going to hope happens, that the next term is smaller. Well, what is the next term? The next term, if this is the current term, 1 over 4n minus 1, we want to know how it compares to the next term, 1 over 4 n plus 1 minus 1, which is 1 over 4n plus 4 times 1 is 4 minus 1 is 3. Now, some of you might be familiar enough with fractions and reciprocals to know instantly which one of these is bigger. Is 1 over 4n plus 3 bigger, or is 1 over 4n minus 1 is bigger? If you're not sure, though, let's build it. Let's build it starting with what's in common. They both have 4n in common, right? 4n and 4n. If I do a minus 1, that's certainly going to be bigger than if I did a minus 3, because subtracting 3 is going to make it smaller than subtracting 1 will make it. Well, we don't want 4n minus 1 and 4n minus 3. We want their reciprocals. When we do the reciprocal, we're also going to flip the inequality symbol. And so 1 over 4n minus 1 is smaller than 1 over 4n minus 3. So it looks like the next term is actually getting bigger. So if the next term is getting bigger, then it's not going to converge conditionally as well. This one is going to diverge conditionally. And so we, unfortunately, I was hoping it would converge. Didn't get there. All right. That is a quick look at series, specifically alternating series. I have seen quite a few comments, though, wanting to go back to doing some more trig substitution and also some more derivatives in first-year calc. Let's do some first-year calc derivatives because we haven't done any derivatives yet. So let's start with that, and then we'll come back and do more trig substitution. With derivatives, what's really important is that you can really recognize the structure of the problem so that you can take the derivative. So let's do an interesting derivative. Let's take the derivative of, let's do the cosine of e to the 4x and divided by, let's see, what do we want to do? Divided by, yeah, let's do the tangent of the square root of x. Lots of things going on here. This one's going to get ugly, but we won't simplify it. What's nice about like the AP calculus test is you don't have to simplify anything. You just have to take the derivative. You just have to do the calculus step. All right. What we've got here is a quotient. We're doing f divided by g. When we have a quotient, we need to use the quotient rule. The quotient rule says take the derivative of the top. The derivative of cosine is negative sine of all of that stuff. But when we've got stuff going on the inside, we have to then multiply using the chain rule by the derivative of that stuff. The derivative of e to the stuff is e to the stuff. But because there's still stuff there, we have to take the derivative of that stuff. The derivative of 4x is 4. So all of that work to take the derivative of the numerator, take the derivative of the cosine times the derivative of e times the derivative of 4x. The derivative of the top then gets multiplied by the denominator, which is the tangent of the square root of x. All right, now we subtract, and the quotient rule then says we take the derivative of the bottom. The derivative of tangent is secant squared of that stuff. But again, because there's stuff in there, we need to multiply that by the derivative of the square root. The derivative of the square root is 1 over 2 times the square root. If you don't know that formula, you can treat that as x to the 1/2 and just use the power rule. But it's kind of a nice one to know that square root, because we do that one a lot, is 1 over 2 square roots. That's the derivative of the bottom. We now have to multiply it by the top, which is the cosine of e to the 4x. And then the entire thing is going to get divided by the denominator squared, the tangent squared of the square root of x. Quotient rule is low d high minus high d low, square the bottom, and away we go. We take the bottom times the derivative of the top minus the derivative of the top times the bottom, square the bottom, and away we go. We could simplify by multiplying each term by 2 root x, but I'm just going to leave that there. That's a beautiful derivative. Keep those questions coming in, though. We want to do log derivatives. You mean logarithmic differentiation? Because that is my favorite integration method. So glad you asked. plant. No, not really. I have no idea who you are on TikTok, but it's still my favorite. So we're going to do it. And then I will promise to get to that more trig substitution. I've seen that comment a couple times. That's coming up in just a minute. But they asked about my favorite topic, so we can't miss it. Logarithmic differentiation. We have to use logarithmic differentiation whenever we want to take the derivative of something that has the variable in the base and in the exponent. If the variable is in both the base and the exponent, the only way we can take the derivative is first get that out of the exponent. How do we get something out of an exponent? With a natural log. We'll take the natural log of both sides because that's going to grab the exponent and move it out front, giving me the natural log of y is equal to x squared natural log of the sine of x. Because now we can take the derivative of both sides of this function. The derivative of natural log of y is 1 over y. But because we're doing it implicitly, we have to multiply by the derivative of y with respect to x. The dy dx, that's what we actually want, and we're actually solving for it. On the other side, you're going to end up with a product. We have a product rule. So we've got x squared, its derivative is 2x, and then we multiply by the other factor, natural log of sine x. Remember, product rule is the derivative of the first times the second plus the derivative of the second times the first. So we're going to have an x squared times the derivative of natural log, which is 1 over the stuff, times the derivative of the stuff, which is the cosine of x. But we're not actually done yet because we are still looking for the derivative of y with respect to x. We want to get rid of this divide by y, which we can do by multiplying both sides of this equation by y. But I don't really want y. What's really nice is y is equal to sine x to the x squared power. We can replace this y with what it represents. And when we do, we get our final derivative, which is dy dx is equal to 2x natural log of the sine of x plus, this is all in parentheses, by the way, x squared. Hey, let's simplify cosine over sine. You know what that one is? That's right, it's cotangent. Times the y, which is the sine of x raised to the x squared power. And that is our solution using differential or using logarithmic differentiation. Excellent. Got a lot of great questions coming in. We're going to do our best to answer as many of them as possible. But if we don't happen to get to your question by the time we wrap up in about 10 minutes, remember, we are here every week. Come in at 4:15 Pacific time, 7:15 Eastern time to make sure you get your questions answered. Mark your calendar, scan this QR code up here in the corner. That way you can join us every week for more calculus questions. And I promised several times, I have promised that I would do trig substitution. So I'm going to follow through on that promise. So thanks for hanging out for that. We're going to do the integral of 1 over x squared times the square root of x squared minus 9 dx. And we're going to solve it by trig substitution, as promised. And then hopefully we'll have time to do a little bit of endpoints integrals as well. Ooh, integral of sine to the 6x. That one looks like a fun challenge. That one might tempt me. We'll see where we fall. Ultimately, our goal with trig substitution is to simplify the square root using a Pythagorean identity. We want a trig ratio squared minus 1. The trig ratio squared minus 1 that we can use is that secant squared of x minus 1 is equal to the tangent squared of x. So we're going to make this into secant squared minus 1 so that we can change it into tangent squared and take the square root. So how do we do that? We're going to make x equal to secant. Well, what about that 9? No problem. We're going to factor it out by multiplying x by 9 as well. X is 9 secant x. Dx then is going to be 9 secant x tangent x dx. Oops, let's not do x. We got to change the variables so we don't get things mixed up. Let's call them thetas so we don't get x mixed up with x. That'd be weird. All right. When we do that, we end up with the integral of 1 over x squared. X is 9 secant, so it's going to be, actually, no, we don't want to do 9. Let me back up. Whoa, 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 whoa. We want to do the square root. Almost made a mistake. Did you catch me in the comments? Can we do a U substitution with trig equations? Those are good problems too. Let's see what we can do. All right, so with the square root in there, because we're going to end up squaring it, x squared then is 9 secant of theta. Then we've got the square root, which has x squared, which is 9 secant squared of theta minus 9. The numerator is our dx, which is 3 secant, oops, I didn't square my secant. 3 secant theta tangent theta d theta. Let's look at how this square root is going to simplify and then how the overall expression is going to simplify. Under this square root, I can factor out a 9, which is going to give me that secant squared theta minus 1. That's what I wanted to be replaced with tangent. So now I've got 9 tangent squared theta, whose square root is 3 tangent of theta. So this has all been replaced with 3 tangent of theta. That's going to become really, really nice because I can reduce out the 3 with the 3. I can reduce out the tangent with the tangent. I can even reduce out a single secant with a single secant, leaving 1 secant left. So now my integral, there's nothing left on top except for the d theta. And we've got a 9 secant theta. Well, this is actually going to be a beautiful integral for us to solve because I can pull the 1/9 out as a constant. And secant, being in the bottom, is the reciprocal of cosine. And we can integrate that. That came out almost too nice. It made me nervous. Let's keep going. Let's see what happens. If it comes out way too nice, we'll double check for an error, but I think I'm good. Cosine, its derivative, antiderivative is sine. Not negative, positive sign. Let's then go back to the original problem where we said x is 3 secant, divide both sides by 3, so we know secant is x over 3. We're going to use that to draw a triangle. Secant is the hypotenuse over the adjacent, which means the opposite side is the square root of x squared minus 9 using the Pythagorean theorem. We want 1/9 of the sine. Well, sine is the opposite over the hypotenuse. We get the square root of x squared minus 9 over the hypotenuse of x. And that, my friends, is our solution to this integral. Trig substitution is so much fun. 9 secant squared theta? Yes. Oh, I think you were mentioning that I missed that squared earlier. Thank you for catching that. You're exactly right. Excellent. Matrices are a lot of fun, but unfortunately that's not calculus, so we're going to avoid that one. I saw an integral that caught my fancy just before that problem. The integral of sine to the 6th. Let's see what we can do with that. Integration always creates the most questions, probably because there's so many tips and tricks that we need to keep track of. It's kind of where all the algebra and all the trig is going to come together. And I might just kind of set this one up more than solve it because there's going to be a lot of pieces to this. The idea of solving this one is sine to the 6th can be rewritten as sine squared to the 3rd power. And sine squared can be rewritten using our power reduction identity. sine squared is 1/2. Whoa, my brown is dying. 1/2 minus 1/2. My brown is really dying. Cosine of 2 theta cubed dx. This is the power reduction identity from trigonometry. Normally we write it as 1 minus 1 cosine 2 theta all over 2, but if we split that up, it usually makes the integration easier. Although this time I don't know if it will. Yeah, let's write it as one denominator. Fine, you win. All over 2. And the reason I want to do that is because I can cube the 2 and get 8 and pull that out. So we've got 1/8 times the integral. And then I can cube this 1 minus cosine 2 theta. Let's look at what that becomes. 1 minus cosine 2 theta squared, I know is going to be 1 minus 2 cosine squared of 2 theta plus, oops, not squared, that's just going to be cosine, plus cosine squared of 2 theta. And then that's going to have to be multiplied by another 1 minus cosine 2 theta. And that's going to be 1 minus 2 cosine 2 theta plus cosine squared of 2 theta when we distribute the 1 through. Then we'll distribute the negative cosine through. And that's going to be negative cosine of 2 theta positive 2 cosine squared of 2 theta. Where am I at? Negative, I'm off screen, but I'm still here, I promise, cosine cubed of 2 theta. So if we combine like terms, we've got negative 2 and negative 1. So we've got 1 minus 3 cosines of 2 theta. Then I've got cosine squared and 2 cosine squared, which is plus 3 cosine squared of 2 theta. And then I've got a negative cosine cubed of 2 theta, d theta. Again, I'm not going to have time to finish this integral, but I'm just kind of setting up, showing how the algebra is going to work. What I would do is I would split this into 3 integrals. I'd stop this integral here and do another integral of the 3 cosine squared dx. And then I do another, or d theta. Oops, I changed my x's to thetas halfway through the problem. Well, that's okay. This cosine squared, we're going to do that exact same strategy again using this exact same formula to expand this out. And so it's going to become 2 separate integrals as well. The cosine cubed, I'm going to pull a single cosine off and change the cosine squared into 1 minus sine squared. And that's going to allow me to do a u substitution to do this last integral. So that's kind of where I would go to finish this off. It's a fascinating integral. Maybe we should start with it next week when we get together. Remember, we are here every week at 4:15 Pacific time and 7:15 Pacific Eastern time on Thursdays to answer your calculus questions. So if you're taking a calculus class, make sure that you mark this on your calendars. Make sure you scan the QR code in the corner here so that you don't miss out on future live events. But we are almost out of time. There have been so many great questions coming in. I didn't have time to get to rectangles. I didn't have time to get to differential equations. So we will take a look at some of that stuff next week. I'll put that at the front of the hour. So make sure you're logging in if you're interested in rectangles, differential equations, logarithmic differentiation, differentials with logs, lots of topics. 4:15 Pacific time, 7:15 Eastern time on Thursday. Scan the QR code so you get reminded. But unfortunately, all good things have to come to an end, and that includes today. But I hope that I made learning calculus a little bit more enjoyable for you. Before you go, don't forget to check out Chegg.com and follow Chegg on all the socials. We're on Twitch, Instagram, YouTube, TikTok, all the things. Hit follow, and of course, follow me at Wallace STEM on all of those as well. Remember, we're here every time at this week, every week at this time. You got that. Thank you so much for logging in, though. It's been a great time with you, and we will see you next time. Until then, happy